Here we'll practice finding the properties of more rational functions. Here our rational function is x to the third power minus 8 over x squared minus 5x plus 6. We'll begin by factoring this rational function on the numerator and the denominator. On the numerator, we'll notice we have x to the third power minus 8. Now, third power expressions are usually fairly difficult to factor, but this one has a particular shortcut. Notice that both terms in the numerator are perfect cubes. We have x to the third power, which, since its third power, is a cube, and 8 is one of our few perfect cubes. Since they're subtracted, we call this a difference of cubes. When you have a difference of cubes, there's a certain trick we can use to factor it. We can rewrite the difference of cubes as a to the third minus b to the third. There's an identity that tells us that if you have a to the third minus b to the third, you may factor it into two pieces, a minus b times a squared plus 2ab plus b squared. The a minus b will be a linear term, and the a squared plus 2ab plus b squared will be quadratic. We'll say that the a term will be the cube root of x to the third, and the b term will be the cube root of 8. Now notice that if we're taking a cube root of a cube, these are inverse functions. This means that we're going to cancel out the cube root and cancel out the cube, and this leaves us with just x for our a term. For our b term, we can go to a calculator and see that the cube root of 8 is 2. Now, if a is x and b is 2, we'll look at our linear term, and we'll say that's x minus 2. For our quadratic term, we'll now take a squared. Since a is x, that will be x squared. Then for our middle term, we'll take 2 times a times b. That is 2 times x times 2. But 2 times 2 will give us 4x. Then we'll take b squared, and then that's 2 squared, so that's also 4. This will be our factored numerator. We'll also factor the denominator because it's second power as well. We'll start with our x squared minus 5x plus 6 and try to think of two numbers that multiply to positive 6. If we try 6 and 1, 6 times 1 would give us 6, but 6 plus 1 would give 7, and that's not a match for the middle term because we want the middle term to be negative 5. 2 times 3 would also give us 6. If we take 2 plus 3, we'll end up with 5. That's the right number, but not the right sign. Therefore, we must use negative 2 and negative 3. Together, that will make negative 5. Therefore, we can split this second power expression into x minus 2, x minus 3. This means that in place of our denominator, we can put x minus 2 times x minus 3. And in place of our numerator, we can put the factored numerator we found using our difference of cubes. This means our new factored fraction is x minus 2 times x squared plus 4x plus 4 on top, and x minus 2 times x minus 3 on the bottom. Now that we factored, we can find the domain by setting the denominator not equal to 0. We say x minus 2 times x minus 3 is not equal to 0. We'll set x minus 2 not equal to 0 and x minus 3 not equal to 0. Now we add 2 to both sides, and we can see that we'll have x is not equal to 2. If we do the same thing to x minus 3, we end up with x is not equal to 3. Based on that, we can draw a number line. We can place our infinities on the left and the right, and place open circles for 2 and 3. This will split our number line into 3 regions, A, B, and C. We'll say that our region A starts at negative infinity and goes to 2, union region B, which starts at 2 and ends at 3, and union region C, which goes from 3 to infinity. This will be our domain for our rational function. We can also use the factored form we just found to find the wholes. When we are looking for wholes, we are looking for identical terms on the top and the bottom. We can see that we have x minus 2 on the top and x minus 2 on the bottom. Those two binomials are identical. When you see an identical term on the top and the bottom, we'll set that term equal to 0. Therefore, we'll say x minus 2 is equal to 0, and if we add 2 to both sides, we'll end up with x equals 2. Now, it's not enough to get that x value. We have to get a y value that goes with that x. In order to get that y value, we'll now cancel out the x minus 2's and look at what we have left. If we cross out the x minus 2, we'll have y equals x squared plus 4x plus 4 on top, and x minus 3 on bottom. Now, we'll let x equal 2 because that's the x-coordinate of our whole. So, when you find a whole, we cancel out the identical terms and then plug in the x that we found. Therefore, everywhere we see x, we now put the number 2. Therefore, we'll have 2 squared plus 4 times 2 plus 4 on top. On bottom, we'll have 2 minus 3. We'll end up with 2 squared, which is 4, 4 times 2, which is 8, plus 4, all over 2 minus 3, which is negative 1. If we take 4 plus 8 plus 4, this will give us 16 over negative 1, and when we divide, we'll get negative 16. This will be the y value for our whole. Therefore, we can say the whole is located at 2, negative 16. Remembering that it's not enough just to give the x, we must also give the y. To answer the next few parts of this question, we can use the simplified form of our rational function, that is, the factored form where we cancel out the x minus 2's. Here we can find the vertical asymptotes for our rational function. Remember that to find vertical asymptotes, we're going to set the bottom of the simplified form of our function equal to 0. So we will not use x squared minus 5x plus 6 for this. We will only need to use x minus 3. We'll say x minus 3 equals 0, and then we'll add 3 to both sides. When we add 3 to both sides, we'll end up with x equals 3. This will be our vertical asymptote for the rational function. Bearing in mind that we already found a whole where x was equal to 2. We can also use the simplified form to find the horizontal asymptotes. Remember that for horizontal asymptotes, we must look at 3 possibilities. One where the top power is higher, one where the bottom power is higher, and one where the powers are the same. If the power on top is higher, we will say there is no horizontal asymptote, but note that there could be a diagonal. If the bottom power is higher, we'll say y equals 0 automatically. If the powers are the same, we would divide the leading coefficients. If we examine our powers of our simplified form, we can see that the x squared is a second power term, and the x on the bottom, since it has no exponent, we'll give it the invisible 1, and we'll say it's first power. This means that the top power is higher than the bottom, and this means our answer for the horizontal asymptote is dne. However, since diagonal asymptote is possible, we'll check for that too. To find the diagonal asymptote for this rational function, we'll again use the simplified form and we'll do long division with it. We'll put x squared plus 4x plus 4 inside and then x minus 3 outside. Therefore, inside of our division symbol, we'll say x squared plus 4x plus 4. Outside, we'll say x minus 3. To begin the long division, we'll look at the leading terms and divide them. This means we'll take x squared over x. If we take x squared divided by x, remember that x has an invisible 1, so we're taking a second power over a first power. This will give us x to the 2 minus 1 power, or first power. Again, we don't have to write the invisible 1, so I'll just write x here. Then we'll take that x that we just found times both terms on the outside. We'll take that x and multiply times x minus 3. X times x would give us x squared, and x times negative 3 will give negative 3x. Now that we've found that, we'll change both of the signs on both of our terms in that x squared minus 3x and write it underneath our x squared plus 4x plus 4. Therefore, the x squared becomes negative x squared. And the negative 3x becomes positive 3x. Now we combine our terms. X squared minus x squared will cancel out completely, and 4x plus 3x will give us 7x. Then we'll bring down the positive 4, and then we'll repeat the process. We'll go back to the top here, and now divide our leading terms again. Our new leading term is now 7x. We'll still divide it by that x, though. If we divide, we'll get 7. Therefore, we'll say plus 7. Then we'll take that 7 times the terms that are on the outside. That's still x minus 3. 7 times x gives 7x, and 7 times negative 3 gives negative 21. But then we'll change the signs on both of those terms. This will give us negative next to 7x, and now positive next to the 21. We'll combine the terms, and 7x minus 7x cancels out. 4 plus 21 will give us 25. This will be our remainder. We know this is our remainder because it's lower power than what we're dividing by. Anytime your remainder is lower power than what you're dividing by, you stop. However, our answer for the diagonal asymptote will be just this x plus 7 that's above the bar. That's our quotient. Therefore, our diagonal asymptote will be y equals x plus 7. There's no need to write the remainder in this answer. Now we'll find the intercepts of our rational function, once again, based on our simplified form. First, we'll find the y-intercept of this by letting x equal 0 and simplifying. Therefore, everywhere we see x, we will instead place 0. Therefore, we'll say y equals 0 squared plus 4 times 0 plus 4, all divided by 0 minus 3. Most of our terms will drop out. This leaves us with only 4 over negative 3, and if we divide, we can write this as negative 4/3. This means our y-intercept will be 0, negative 4/3, bearing in mind that we set x equal to 0, therefore x must stay 0, but y will be negative 4/3. In order to get the x-intercept now, we'll set the top equal to 0 and try to solve. We'll now set x squared plus 4x plus 4 equal to 0. Now let's think of two numbers that multiply to 4. If we tried 4 times 1, that would give us 4. But if we take 4 plus 1, that's 5, and that's not a match for the middle number because we want positive 4x. Therefore, we must use 2 plus 2. 2 times 2 would give you 4, and 2 plus 2 would also give you 4. That's a match for the middle number, and so we'll factor this into x plus 2 times x plus 2. We may also write this as x plus 2 squared if you wish. In any case, we'll let the inside become 0, and we'll say x plus 2 equals 0, and if we subtract 2 from both sides, we'll get x equals negative 2. Therefore, for our x-intercept, we'll say x is negative 2, and since we're looking at the x-intercept, that means y is automatically 0. This means we now have an x-intercept of negative 2, 0, and also a y-intercept of 0, negative 4/3. Now that we've collected all of our information about the asymptotes, intercepts, holes, and domain, we can create a sign chart. As always, when we create our sign chart, we will mark the x-intercepts and vertical asymptotes. Note that the x-intercepts will always be closed circles, and the vertical asymptotes will be open. We'll begin by drawing the number line, and we'll place infinities on the left and right. We'll place a closed circle at negative 2, 0, and then we'll place an open circle at positive 3. This will split our number line into 3 regions, A, B, and C. In region A, we'll select an x that is between negative infinity and negative 2. We'll try negative 3. Our y in that case will equal negative 3 to the third power minus 8 over negative 3 to the second power minus 5 times negative 3 plus 6. On the top, if we take negative 3 to the third power, we'll get 27, but it will be negative because a negative number to the third power is still negative. Negative 27 minus 8 will definitely give us a negative answer. It turns out it's negative 35. On the bottom, negative 3 squared is positive 9, negative 5 times negative 3 is positive 15, and then plus 6. This will give us positive 30 on the bottom. Negative 35 over 30 is a negative answer, which means region A will be negative. Now we move on to region B, and we'll pick an x that's inside of region B. Now we may note that in region B we will also have 0, and we have some information about 0 already. We know that when x equals 0, y will equal negative 4/3. This means that everything within region B must also be negative. Therefore, we'll mark region B with a red circle here and show that it's negative. Then we move on to region C. We'll need to pick an x value that is greater than 3, and we'll use x equals 4. Therefore, when we find y, we'll take 4 to the third power minus 8 over 4 to the second power minus 5 times 4 plus 6. 4 to the third power is 64. Minus 8 will give us 56. We'll divide this by 4 squared, which is 16, negative 5 times 4, which is minus 20, and then plus 6. If we take 16 minus 20 plus 6, we'll get positive 2. Therefore, we have 56 over 2. That will give us a positive answer, which means region C must all be positive. Now that we have our sign chart, let's try to draw our graph. We'll begin drawing this graph by marking the asymptotes. We'll begin with x equals 3, which will be a vertical asymptote. We'll draw a vertical line right here at 3. Then we have a diagonal asymptote. To draw this, we're going to have to draw a diagonal line starting at 7 on the y-axis, because 7 will be our y-intercept. We'll first mark that somewhere on the y-axis and mark that as 7. Then we'll need to draw a diagonal line that has a rate of change of whatever number is in front of x. Since we have no number in front of x, we'll place the invisible 1, and that will be our rate. And we'll draw a diagonal line with that rate. We'll also place the intercepts and holes on this picture now that we've placed the asymptotes. We have a hole at 2, negative 16. If we label our x-axis with a 1 and a 2, and then we'll go down here to negative 16 and place an open circle. We'll also place an x-intercept at negative 2, 0, so we'll mark the x-axis negative 1 and negative 2 and place a closed circle in that position. We also have a y-intercept at 0, negative 4/3, so we'll put another closed circle fairly close to the axis here. Now, it may be a little bit tricky drawing a curve. To draw this curve, we're going to start on the left side with an arrow. It will be fairly close to the diagonal asymptote. Now we're going to draw this line more or less parallel, but not exactly parallel, to the diagonal asymptote, and allow it to cross through negative 2, which is our x-intercept. Now, we have no other x-intercepts. Therefore, this line must now turn around and go back. If the line had crossed straight through, there would have been another x-intercept. Since we don't observe that, we're going to touch the axis at negative 2 and come downward. We're also going to make sure we cross through the y-intercept, which is the other closed circle. So when we draw our graph, we must cross through all closed circles. And then we're going to turn downward and hit this open circle as well, and continue on down toward negative infinity. The reason why we know to do that is because region A and region B are both negative. There is no way for the line to become positive in those regions. Therefore, we must stay below the axis here in order to match what our sign chart says. Then, in region C, we're going to turn positive. So we must come in from positive infinity. We're going to run along the vertical asymptote, and at some point we're going to turn and then follow the diagonal asymptote. Figuring out exactly where that part of the graph turns and switches over to follow the diagonal asymptote is beyond the scope of Math 171. For those of you who are in the engineering program, you'll see more about this next year. For now, it's good enough just to draw a rough sketch of the line following the asymptotes for region C. And so now we have our sketch of our graph for our rational function.